Hi, everyone. I think that we are now broadcasting. Great, so I'm live now. Well, thank you very much for joining me. Let me just tell you a few words about myself. I'm Salakhutdinov. I did my PhD at the University of Toronto with Jeff Hinton as my advisor. Was very lucky to have him as my advisor. Once I finished my PhD, I spent a couple of years at MIT working with Josh Tenenbaum on sort of one-shot learning and human-like learning. After that, I spent about 4 years at University of Toronto as a faculty, and then last year I moved to Carnegie Mellon as an associate professor there. And also last year, I started working at Apple as a director of AI research. So my area of research is deep learning. I worked a lot on optimization, Boltzmann machines, various deep learning models, and more recently, started looking at multimodal learning, language understanding, as well as reinforcement learning. So today, what I'd like to do, let me start sharing my screen. Today, I'd like to talk about some of the recent advances and some of the key challenges in deep learning. And then once I finish, probably talk is going to be about 25, 30 minutes, and then we'll go to questions. The talk is not going to be very technical, but what I'd like to do is I'd like to tell you some of the key challenges that we're facing in machine learning and in deep learning in particular. Okay, so if we look at what we've had in the last decade, right? We've had a massive increase in the computational power as well as the amount of available data. So if you look at images and text, if you look at language, just go and get language from the web, speech and audio, gene expression data, recommendation systems, relational data, social networking data, as well as scientific data. One of the key questions we're all trying to ask is how can we extract interesting structure from all of that data? And one way of doing it is building these hierarchical models, these deep learning models that can extract a structure as well as perform inferences at multiple levels of representation. And I'll tell you a little bit more precisely what that means. If we look at the impact, the impact of deep learning has been quite substantial. If you look at speech recognition, pretty much every major IT company is using speech recognition as using deep learning in its speech recognition systems. Computer vision, recommender systems. More recently, we're beginning to see more and more advances of deep learning in language understanding, which I'll talk a little bit more about, as well as in places like drug discovery and medical image analysis. Those are the areas that are coming up lately in terms of deep learning applications. Now, what do we want to do? Ultimately, we'd like to build AI, right? We'd like to develop computer algorithms that can see and recognize objects around us, algorithms that can perceive human speech, understand natural language so that they can communicate, as well as navigate around autonomously, as well as display human-like intelligence, right? And you'll see right now there's a lot of kind of application areas in the space of personal assistance and driving cars and such. Now, here's an example of the speech recognition technology. This is an example that was provided to us by our friends at Microsoft. So if you see back in 1980s, the speech recognition has been steadily improving up until about 2000. So on the y-axis, you're looking at word error rate on a particular data set. And pretty much for the last, from 2000 up to 2010, nothing was really happening. So the speech recognition technology was kind of, it was working, but it was never working good enough. It was never good enough to actually be deployed in products. And over the last 5 years or so, we've seen a huge increase in performance or decrease in the error rate using deep learning algorithms. Neuroimaging, that's another area. This is an example where I was collaborating with some folks at the University of New Mexico of trying to understand as well as model, in this case, fMRI data using something that's called restricted Boltzmann machines. We've had some successes in terms of figuring out what the right features so that we can do proper classification. So that's one example. If you're interested, you can look at the paper, which is available online for you can just download it online. Now, today, what I'd like to do is I'd like to talk about some of the key challenges. Where are we struggling, and where are we making a little bit of advances? Multimodal learning is one big area of research. So this is the area where you're trying to combine multiple sources of data. Imagine learning representations from images and text, or from video and sound, or typically in a lot of different application domains, you might have lots and lots of different modalities that you're trying to fuse together. I'll show you some examples of that. Reasoning, attention, and memory. This is something that we see more and more in deep learning. How can we build systems that can reason, that can attend to the right parts of information, as well as how can we have systems that have memory? I'll show you some examples of that. Language understanding, natural language understanding is another big area, and reasoning and natural language understanding is something that's extremely important. And again, through this presentation, I'm going to show you some examples of that. Reinforcement learning, deep reinforcement learning, has evolved in the last few years as a dominant technique where people are looking at developing algorithms that perceive the world around us and try to take actions. Reinforcement learning has been around for a very long time, but just recently, with the advances in deep learning, that area is being revived a lot. Also, in the areas of unsupervised learning, one-shot learning, and transfer learning, right? So building systems that can learn from few examples, or building systems that can leverage previously learned knowledge so that they can start learning new tasks much faster, right? That's the area of transfer learning, one-shot learning, and unsupervised learning. How can we build models that just look at unlabeled data and able to extract interesting structure from the data? Let me start with multimodal learning and attention mechanisms. So one particular area of interest to a lot of us is image understanding. Right, so given an image, can you tag what's in the image? And you can build a model like a convolutional neural network that predicts what's going on in the image. Right? So here it tags the image as strangers, co-workers. You can think of it as a simple classification problem. Now you can go beyond that and you can say, can I actually build a system that can generate in natural language a description of what's going on in the image? And one way of doing this would be to find a nearest neighbor image. So find the closest image in your database and just copy the corresponding caption, right? And that is what the model does. It says people taking pictures of a crazy person. But if you're actually building a statistical model, this is what the samples from the model would look like. A group of people in a crowded area, a group of people are walking, talking, and so forth. So you can see that, this is the research has been happening in the last 3 years or so. And it's remarkable that, pretty much no one expected these models to work so well. Here's an example of where the model works, remarkably well. It was done back in 2014. A car is parked in the middle of nowhere. There's a cat sitting on the shelf, a little boy with a bunch of friends on the street. So you can see that it's remarkable. And again, it was surprising back in 2014, and multiple groups that were pretty much solving the same problem. But it was surprising to a lot of us that, these models could do so well. Here's an example of the model not doing so well. So for one example, it says the two birds are trying to be seen in the water, or the handlebars are trying to ride a bike rack. Now, if you look at these two images, you might say, well, that's not good. But at the same time, to us as researchers, this was actually a really good result, because what we wanted to see is we wanted to see a model that can generalize. We wanted to see a model that can generate new captions. Obviously, a caption like the handlebars are trying to ride a bike rack is something that a human wouldn't generate, right? Because it just doesn't make much sense. But in terms of generalization, the model wasn't just copying sentences from the training data and just kind of doing sentence retrieval. It was really trying to generate new descriptions. And then you get you get sort of examples like this: a man holding a red apple in his mouth. And the reason why we see these kinds of captions is because the model was never trained on images of sports, right? So sports images is something the model has never seen before. So if you give it some examples that outside of the training sort of domain, you kind of see these funny examples. And that's something to keep in mind, that these models are not very good in terms of generalizing to completely new domains. And there's an active research area of research as well. And generally, when you think about these systems, you can think about what's happening is that you have an image, you encode it using convolutional neural network into some feature space. Typically, it's a continuous feature space, typically 300 or 500 dimensional feature space. And then, given the feature space, you decode it using recurrent neural network or language model into the sentence. So you can learn a joint embedding between images and text. You can pretty much embed anything. You can embed images, words, sentences. There's also a very natural definition of the similarity, which is just looking at a dot product between the vectors and the semantic feature space. But a lot of systems, a lot of caption generation systems are based on this idea. And again, you can embed a number of different things. And there's been a few papers that effectively, it's a very powerful way of trying to merge different modalities together. You're bringing them to the same representation into the same low dimensional vector space. And this is what the multimodal linguistic regularities might look like. So if I have an image, I project it to the semantic space. So I extract its 500 dimensional features. I take the word flying, and again, I extract its 500 dimensional features. So I subtract the flying, I add sailing, and I look at the nearest neighbors, and I get sailing boats. Or if I take these kittens and I say minus ball plus box, I get kittens in the box. Or I have a kitten in the box. When I say minus box plus ball, I get kittens in the ball, right? So this was one example. It doesn't work perfectly on every single concept, but it does capture a lot of sort of regularities and understanding between pixels and images. The other thing that you can do is you can look at generation with visual attention. This was done back in 2005, but this was the first step towards trying to combine visual attention and caption generation. So in this particular example, you have an image and the system generates a man riding a horse in the field. And again, you have essentially a convolutional neural network followed by a recurrent neural network with attention mechanism. So here, when I say a man, it focuses on the man. You can see here, riding a horse, it tends to pay attention to the horse in the field. It looks at the field. And this was an interesting development, because after that, we start seeing a lot of different research in the space of visual question answering, where people are trying to get the system to answer questions about images and such. There's a lot of research happening in this space. But what's interesting is that it allowed us to try to understand why the model would generate certain captions, particularly captions that wouldn't make much sense. So for example, this is a caption of a woman holding a clock in her hand. And so when you look at the word clock, it focuses on the pattern, the t-shirt pattern of the person. And so it confuses the pattern with a clock, right? Well, this is another example, a large white bird standing in the forest. So if you look at when it generates the word bird, it actually zooms in and confuses giraffes with a bird, right? Because it's pretty much confusing. This must be a forest, and we have birds in the forest. So it gives us a little bit of explainability why the model does what it does. And we'll see more attention when we look at models related to reasoning and reading comprehension. But that's another active area of research. And if you look at this paper, there is a code data sets. You can download the code and apply these models to your problems. Now, we've talked a little bit about multimodal learning as well as attention in the space of images and text. But what I'd like to do now is I'd like to talk about reasoning attention and language understanding. Here's an interesting example where we're training a recurrent neural network on 11,000 books and using 74 million sentences. So there is no supervision, there is no label of data. We're just trying to extract statistical structure from words and co-occurrence of words using RNNs. And here's an interesting thing that you can do with this model. You can train the model on 7,000 romantic novels. So you're building encoder and decoder that can, understand and generate sentences. And then you can hook up a caption generation system. So given this particular image, you can ask the system, can you generate me a sequence of sentences that somehow correlate with that image? And this is what the system does. She was in love with him for the first time in months, so he had no intentions of escaping. The sun had risen from the ocean, making her feel more alive than normal. She's beautiful, but the truth is I don't know what to do. The sun was just starting to fade away, leaving people scattered around the Atlantic Ocean, which is kind of funny. Semantically, it doesn't make much sense, right? Because it talks about the sun had risen from the ocean and then the sun just starting to fade away. But if you look at the syntactic structure, it's actually pretty good. Right? It doesn't make a lot of mistakes. And again, this model didn't have any notion of linguistic knowledge. It had no notion of the meaning of different words, no notion of prior knowledge, just by looking at co-occurrence of words and trying to build essentially a predictive model of sentences. Now, what you can do is then you can build a system that's kind of looks at semantic relatedness, right? So this is an example where it's a very important example where I give you two sentences and I have to tell you, do they mean the same thing? And that's an important, task to do when you're trying to do sentiment analysis, when you can try to understand what's in the document and so forth. So in this case, a man is driving a car is being driven by the man. The system basically says it's the same. You have a score of 4.9, it says it's the same sentence. The meaning of the sentence is the same. Here's another example. A girl is looking at the woman in costume, or a girl in costume looks like a woman, so it's different. The model assigns it a low score. So clearly that basically says there's some similarity between these two sentences. They're not completely arbitrary two different sentences, but they don't really mean the same thing. Here's an example where the model is failing, right? So it's thinking it's the same. A person is performing tricks on a motorcycle. The performer is tricking a person on a motorcycle, right? So you can see that here you need to do a little bit better, and the model is actually failing. But you can see these sentences are kind of interesting, right? The performer is tricking a person on a motorcycle is an unusual sentence to have. Now, when we start going into systems that are much more complex, or you can think about, the next step is trying to build algorithms that can reason, or that can understand something about the context or something about the document. Let me show you an example of an interesting data set called Who Did What data set. So here are a couple of sentences. It's a whole new story. But this is an example where you basically say, it talks about arrested Illinois Governor Rob Blagojevich and his chief of staff John Harris on corruption charges and so forth, included Blagojevich allegedly conspiring to sell or trade the Senate seat left vacant by President-elect Barack Obama. I don't know if you remember, in the US in 2008, there was a big scandal where Rob Blagojevich was doing some shady stuff in order to sell Obama's seat in Senate. But if I give you this news story and then I give you a query, right? And the query says, President-elect Barack Obama said on Tuesday he was not aware of alleged corruption by X and so forth. The question is, who is X? Is it Barack Obama? Is it Rob Blagojevich? Is it John Harris? There's a whole different, different answers that you can answer, and the answer is Rob Blagojevich. Now, if you look at these questions, these questions require a little bit of reasoning, right? You can't just look at a particular matching between the words and find out one particular sentence in the context on a document in order to be able to answer that particular question. You actually have to look at multiple sentences and be able to do a little bit of reasoning to answer that question. And that's one big area of research, and people are really good at doing that. People have no problem kind of answering these questions because we're very good at doing inferences and doing some reasoning. And now, if you look at what these systems are doing, these systems are relying on recurrent neural networks, right? And the way that the recurrent neural networks are working is that you have a hidden state at the previous time. So that's the hidden state. It's a summary of what happened up to the previous time step. You have an input at time step t, so that could be a word, for example, in a document. You combining both of these representations, they go through nonlinearity to produce the next hidden state. So that's illustrated in this picture here. So typically when we look at the documents, we have a sequence of words. So we encode the sequence of words using recurrent neural networks. And if you look at what these systems are doing, these systems are much more complicated. So if you look at the first layer is essentially looking at embedding of the words using something that's called word-to-vec representation or blah-blah representation. Then you feed it into recurrent neural network, which essentially tries to understand a little context around the words. You also have a query, and a query also is encoded using a recurrent neural network, something that's called gated recurrent units. Then you combine both of these representations. It's essentially coming up with some representation of whether the query matches some of the tokens in the document, and that's the first layer representation. It goes to the second layer. The second layer filters up some of irrelevant information, but aggregates more relevant information, and so forth. The point that I'd like to make here is that you probably are familiar with neural networks or with convolutional neural networks because you've had some of these lectures before. You can think of these models as kind of going beyond your standard convolution or your standard neural network architecture, where you actually at every single layer you have a recurrent network, which kind of looks at the temporal information, looks at the overall document, filters up the relevant pieces, the relevant sentences, goes to the next level and propagates information all the way up to the top. So we see more and more development of these more complex architectures that are combining sort of deep learning with recurrent neural networks. The interesting thing is that when we look at attention, what's happening is we can basically figure out that in this particular example, the model is basically paying attention to different parts of the document. So for example, at the first layer, it picks up that alleged corruption highly correlates with Governor Rob Blagojevich. And the second layer, basically Senate seat correlates it with Rob Blagojevich. So it picks up a few different features, important features, in order to be able to answer the question correctly, which is kind of interesting. And we see a lot of that being happening across, a lot of different examples. And this is something that we're not really telling a system, pay attention to this and this, these are important features. The system basically figures out what are the important features to pay attention to so that I can answer the question correctly, right? So it's kind of learning what to pay attention, much like we've looked at attention mechanisms for visual caption generation. And there is now a lot of research is how can we incorporate prior knowledge, right? How can we take the text and look at the word relations, look at the entity relations, look at co-reference, dependency parsers, in order to be able to build a much better representation of text through typically these recurrent neural networks. So that's a very active area of research. A lot of us don't know exactly how to do it. A lot of previous work just relied on just not using any prior information, but just mining as much as we can from text. But now we also try to figure out, can actually prior information help us? Here's another example of trying to incorporate something based on prior information. So imagine I give you these three sentences. Mary got the football, she went to the kitchen, she left the ball there. So I can build a recurrent neural network that analyzes the sequence of sentences, but I can also use co-reference, right? I can try to say, well, Mary, she, and she, that means the same thing. So that should help me answer any questions that I might have about Mary. I can also incorporate synonyms, right? The football and ball, they refer to the same thing. So generally, there's been some work in my lab as well as in other labs of how can we incorporate that prior knowledge, right? So we can construct something that's called memory, and we can look at converting these graphs into acyclic graphs. And there is a paper that basically describes how can we make the structure more efficient and just basically fold it into an RNN model. And that actually gives us some substantial gains when we look at, question answering or reading comprehension type of tasks. Now, in the last 10 minutes or so, in the last 5 or 7 minutes, I'd like to tell you a little bit about reinforcement learning, because I think that that's the area of research where there is a lot of activity and there's a lot of exciting developments. So in the setting of reinforcement learning, what you're trying to do is you're trying to learn behaviors. So you're trying to learn to map sequences of observations to actions. And the way you can think about that RL is working is given an agent, the agent takes the action, the environment gives you back a new state or a new observation, and once in a while you get a reward. Typically, that's a sparse signal, but the reward tells you, was that action good or bad? Now, if you look at deep reinforcement learning, essentially what we're doing is we're just basically sticking a deep neural net that, given an observation, typically it's a high dimensional, could be image or a sound or a multimodal input. It passes through the deep neural net, and then you're producing the action. The action could be, move forward, move back, turn left, turn right, for example, if you're building a little agent that navigates around in the environment. Now, one big area of research, and to me it's as exciting area of research, is trying to get these systems to have external memory, and in particular a learned external memory. How can we build a mechanism when we can have this external module that we can write to and they can read from, much like our computers are? But the interesting thing here is that you're trying to actually design algorithms that are learning what to write and are learning what to read from the memory. There's been a lot of interesting work coming from Alex Graves on differentiable neural computers and neural Turing machines, which kind of laid the foundation to this work. But before we sort of get into the representation of the memory, let me actually show you a simple application of deep reinforcement learning. This is learning to play a 3D game without actually memory. It was a AAAI paper that appeared this year. So this is a deep reinforcement learning in 3D environments. So here what you're trying to do is a Doom environment. You're trying to learn to navigate. It's a very simplistic environment. Obviously, you can see the input are the frames. The output is the action, move left, move right, move forward. And the reward is collect as many objects as possible. So the interesting thing about this work is that you're not telling the system how to navigate. You're not telling the system, move left, move right. You're just telling the system, collect as many objects as possible. So every time you collect an object, you get positive reward, right? And the model remarkably is able to just, from that signal, it's able to navigate in this environment, much like humans would learn to navigate, right? And then you can train this agent to navigate in completely, different environments, different maps. And again, the task is to collect as many objects as possible. Sometimes it gets stuck, but as learning proceeds, it does quite well. The remarkable thing is that once you get the agent and you put it in completely new environment, right? So this is an environment that the model has never seen before. The model has no problem being able to navigate in this environment and doesn't really, it can just basically move around in the environment and doesn't have any problems in terms of solving this new task, particularly moving in a completely new environment. But the problem with these kinds of systems is that they are very reactive, right? You see your input, which is your state, your frame, the image, and you just take an action. There is no notion of memory. There is no notion of where you've been. So you can't really do any sort of planning, or you can't really, solve any long-term dependency task. It's very reactive. I see, I act. So what I'd like to do is I'd like to tell you a little bit about the memory. So imagine I give you the following example. It's a sort of toyish example, but it's extremely hard to solve. Imagine that I give you an indicator, and the indicator is either blue or pink. If the indicator is blue, I have to find the green block. If the indicator is pink, I have to find the red block. Now, the model has to figure out that there is something that's called an indicator. And it has to figure out that I have to remember the state of this indicator in order to be able to find the right target, right? And this is a fairly difficult task because this is, the distance between when you observe something and the target can be quite large. And again, we're not telling the system that there is something that's called an indicator and this is where you have to go. So it has to figure out these sort of rules, these causal rules on its own. And obviously, if we were to tell our agent, these rules, the problem would be very easy to solve. The real task is, can the agent, by looking at the environment, figure out this sort of causal relationship? And what we do is we do the following. Given an observation, we extract the representation, and then we write it into the memory at a specific location of where the agent is, and then we take the action. At the next time step, there is a read operation with attention mechanism. So it reads the parts of the memory that the model decides to be important. It writes back into the memory the important information, and then it takes the action, and so forth. So you can see that, there is this memory block that keeps being updated, and we're writing, we're reading from it, and we reshape this memory as we navigate in the environment. And this is what the system is able to do. So it finds that there is a wrong indicator, which is, there's a blue indicator. It goes to the wrong target. It figures out it's the wrong target. It backtracks, and it navigates again in this environment. This is sort of a 2D environment, a 3D visualization. It goes around, it tries to navigate in the environment up until it finds the right target, right? So this is an instance, a very simple example but it's extremely difficult to learn, of this long-term dependency task. And the model was able to successfully learn the memory, successfully learn the state of the indicator, and successfully learn to retrieve it retrieve the right part of the memory where the indicator is, in order to solve this task. And really, what we're trying to do is we're trying to build systems that can also learn to reason and communicate. Here's another example of a system where we were trying to build an agent that can learn to ground the language, or can learn to execute instructions, right? So this is a setting where we say, go to the green torch, or go to the short object. So the model is actually learning to ground a language. It's in very early stages. It's very simplistic task, but then it starts learning things like go to the smallest blue object, right? Or go to the tallest object, and such. So it starts, or go to the shortest object. So it starts understanding something about the meaning of the word shortest, or the meaning of the word tallest. And after some type of a lot of learning, it's actually doing quite well in terms of understanding, in this constrained environment, the meaning of these simple words. And ultimately, we want to be able to build systems that can have this external memory, that can remember, so that they can plan in this partially observed environments. There's also systems that can reason and communicate, particularly in the multi-agent environment, where we can, be able to communicate with humans, communicate with other agents, and build our own knowledge base. So that's something that's, a lot of research is taking place in that space, and that's a very, very exciting area of research. One final note is the drawback of many of the existing methods that I've shown you today is that they require a lot of learning. And right now, in virtual environments, we can do that. But again, in order to be able to build these systems and be able to deploy them in real environments, we need to be able to come up with algorithms that allow us to learn from fewer examples or fewer experiences. And that's, again, an active area of research. How can we get our systems to leverage some prior knowledge so that we don't have to relearn new things from scratch? And again, that's something where there hasn't been a lot of breakthroughs done in this area, and that's an exciting area of research as well. On that note, let me say thank you, and I can take a few questions. The question is, let me just quickly browse through. Yes, the slides are going to be available. I'll make sure that they're converted to PDF. I'll put them online for people to look at. Just the first question. Let's look at the first question. What's the current state of the art in creating embeddings of entire documents? Yeah, that's a good question. So right now, there is a way, the most common way of creating embeddings of the whole document is typically, the traditional way of doing it would be to use TF-IDF. You have a bag of words representation. You collapse it into bag of words. You lose all the temporal information. You just build a neural net to get the semantic representation or some vector-based representation on just TF-IDF bag of words features. Now there's been some work on using RNNs. So what you can do is you can use bidirectional RNNs. You extract, you read documents from left to right and right to left, and then you aggregate the states of RNNs in some way. Sometimes people take the first and the last sentence. Sometimes people use attention-like mechanisms to construct some fixed dimensional representation of the document. So that's something that people, I believe, have done and is the current state of the art. The second question, how these rewards assigned tasks are formalized for learning, ARL and papers? Yeah, so the way that's actually a very good question for RL. How do you set up this reward structure, and that's up to the modeler. And this is something that's called reward shaping. If you look at some of the papers called reward shaping, there's a lot of work, because that's an excellent question. There isn't a very clear way to say, how do I set up the rewards? And reward shaping is a very important area of research. So, for example, in the case of Doom-like environments, rewards, collecting objects was a good reward. There is depth estimation. Can you predict the depth? That's another kind of reward that you can set up. People are trying to look at other types of reward structures where basically say, I give you a reward if I move into new place. So kind of like almost like trying to figure out how to you're basically trying to figure out how to build systems that are curious, right? So there's a lot of reward shaping happens in this space. Let's look at the next question. Embeddings are very general and usable in a lot of tasks, but flexible size vectors can only capture so much. Attention is great, but still far seems to be largely used for tasks which is generate text. Is there something between these two, say classification or finding related items? So yeah, that's a very good question. Typically, it depends on what your tasks are. If you're interested in retrieval, right? How do you retrieve, let's say, given a question, how do you retrieve the relevant articles that can answer that question? Then to some extent, having a fixed length representation of a document might be a good one, because you can just do dot product between those vectors. I don't think there is anything has been in the middle that kind of that you're alluding to. Generally, I can tell you from some of our work, we've looked at the question of given a question, let's say I give you some question and I have 20,000 Wikipedia articles, right? How do I answer that question? And we found that, a pretty good way of doing that would be to use something that's called semantic retrieval, the work that we've done a long time ago, back when I was at the University of Toronto. Basically, the idea is that, you can use key values, some of the traditional information retrieval methods. You can also compress documents into the fixed length representation, and also retrieve, quickly retrieve maybe a candidate's, 10 or 20 different candidates of where you think the answer might be. Once you retrieve these 10 or 20 candidates, then you can do the reading comprehension task. You can really go through using attention mechanisms and try to match the query with every single sentence in the document. It's a process that requires some time, but you can run a lot of it in parallel. So this is kind of something in between, where you have a corpus of 20,000 Wikipedia articles. You're using fixed-based representation, fixed-length representation of the documents, also using some traditional information retrieval techniques, like looking at the key values. You narrow it down to maybe 20 articles, and then within 20 articles, you do reading comprehension task, which is kind of looking at the query and trying to look at the attention mechanisms and trying to really come up where the answer might be. Again, if you can parallelize it across multiple machines, it can be pretty fast. What do you think will be the first few practical use cases, techniques you covered? So in terms of practical cases, I agree with you. So obviously for caption generation, I believe that Facebook has already rolled it as one of the features for folks who can't see, right? Imagine I'll send you the picture, and if you can't really see, the system can automatically generate a few sentences describing what you're seeing in the picture, which I think is pretty interesting. When we look at reasoning and when we look at question answering, obviously there are applications. There are applications, obviously for question answering, right? If I ask, you think about personal assistants. If I ask a question, and typically intelligent question that requires you to look at a few sentences, or it requires you to look at the overall document and come up with the right answer, obviously it can have big practical applications. There's been some work I know in the academia where, I give you a question and I give you like a Ubuntu manual, right, about Ubuntu operating system. The real task is, can you build a machine that looks at the technical content and comes up with the right answers, or maybe a set of possible candidate answers. right? Which is kind of very cool, right? You know, if you ask the question, well, I have a segfault here and here, and I can't really compile this, what do I do? You have an algorithm that looks at your Ubuntu manual, the operating system, and comes up with the right answer. Wouldn't that be amazing? So there's some work happening in that particular space where you know you get to have algorithms that can reason. In the space of reinforcement learning, there is a lot of work, and people are just at this stage are working mostly in virtual environments, but we're all trying to figure out how can we go from virtual environments to the real environments, which is definitely a challenge, right? So that requires some notion of domain adaptation and such. Base paper to learn bidirectional RNNs with attention mechanisms. You should actually look at, if you actually Google bidirectional RNN with attention mechanisms, you know, there's going to be a lot of papers. The best papers to look at, there was a paper coming out from Yoshua Bengio's group back in 2014 by Dmitry Bakhnadou, who actually introduced the attention mechanism, right? So I would recommend looking into that. I think it was back in 2014. If you're also interested in sort of attention, there is a paper that I cite in this particular presentation by Kelvin Xu on using attention mechanism for visual caption generation that also describes two different attention mechanisms, soft attention and hard attention. So you can look at both of them. Maybe just a few other questions. Many of the architectures are hard crafted, fine-tuned. Do you believe there are limits to human-crafted architectures to solve AI problems? More, you know, can you design more sophisticated handcrafted architectures? Yeah, it's a very good question, right? So sometimes people joke that, you know, before kind of a deep learning era, what we were doing is we're kind of trying to come up with the right features. So we were handcrafting features, right? You know, do I, you know, use this feature for pixel? Do I use this feature for audio signal and so forth? And now in kind of this area, we're tweaking architectures. Now it's all about, do I tweak this architecture? Do I tweak this architecture? I think there are going to be limitations to that. At the same time, you know, we still don't have very good understanding of what architectures are working better and what don't. You know, back in 2009, 2010, having an architecture with 3 hidden layers or 4 hidden layers, people thought, well, that's a lot, right? That's a lot of architectures. And then there was a paper by Alex Krzyzewski and Hinton's group, Jeff Hinton's group, that basically showed, I think it had like 9 or 10 layers that won ImageNet competition. And people thought, wow, it's 9 layers. That's a lot of layers. And then in 2013, Google came up with an architecture that had like 23 layers. And people thought, well, 23 layers, that's a lot of layers. But the results kept getting better and better. And then in 2015, 2016, residual networks paper out of Microsoft Asia came up, and they had 151 layers, right? So, you know, it's kind of funny. And then, you know, people are, maybe we're saying, maybe we don't need 151 layers. Maybe we can go back to 30 layers. And so a lot of it is really right now, people are trying to figure out what architectures to use. One thing that is common is that it seems to be that we need a number of processing steps, particularly for visual domain, to be able to classify or to be able to do reasonably well in terms of generating captions. So, which basically means that we need multiple layers, multiple hidden layers, because that's how we do processing and that's how we do compute. But ultimately, maybe we can design more intelligent algorithms that can adapt their own architectures for tasks, for particular tasks that we're trying to solve. There's been a few papers on that, where people are designing different modules, and then when you're trying to solve a particular task, we're trying to come up with different ways of pulling these modules together. So that's a very interesting work. We just don't have good ways or good optimization algorithms to do that, right? A lot of it is kind of brute force and not very elegant at this point. So let me just see, can DeepRL be used in NLP tasks? If yes, can we formulate the problem to include for the RL agents? Yes. So deep reinforcement learning for natural language tasks. One area where DeepRL is we're seeing some examples is in dialogue-based systems. right? So imagine the situation where I'm trying to talk to a machine. I ask the question, and let's say a machine can just answer the question, which is what a lot of question answering systems are doing right now. I ask the question, machine has to answer the question. But now imagine that the machine, instead of answering the question, it can choose to take an action, and the action could be ask a different question. Or maybe, you know, a machine could say, well, I have these 5 questions that I could follow up to ask if the question that I'm asking is vague, what that question should be. So that's exactly what would constitute a reinforcement learning agent that would have to choose what question to follow up. And this is, again, a dialogue-based system. Imagine I'm asking the question, and the machine basically asks me a follow-up question. I say, okay, I'm asking the next question. The machine asks me a follow-up question, and so forth. So the conversation doesn't just go me asking the question, the machine just gives me the answer, right? So this is you have multiple turns, and at every single turn, a machine has a certain action to take. It could be, you know, ask this question or that question or that question. So this is where reinforcement learning is really being used right now, and there's been a few papers in that domain. There is some research happening at Carnegie Mellon as well, in my group, where we are really trying to figure out how to use RL in the conversational agents, right? So not much in terms of classification, reinforcement learning, but in terms of building these dialogue-based systems and kind of conversational agents is where we see application of RL. Tell us something about the work that you're doing at Apple. So I can't really tell much about what's going on at Apple, but the interesting thing is that at Apple, I can say that, you know, there's lots and lots of different machine learning areas, you know, ranging from vision, computer vision, ranging from obviously speech recognition, language modeling, health understanding. So one of the interesting things for me at a place like Apple is that, you know, there is a lot of, you know, you'd be surprised how much machine learning and applications of machine learning you see in the organization. And that's true, I think, for a lot of different IT companies. It's true of Google and Facebook as well. So, you know, pretty much every single piece within Apple as a company, within every corner, you basically have machine learning engineers, machine learning, researchers doing interesting things. So use LSTMs instead of RNNs in NLP. So when I was maybe I wasn't clear during the talk. The question is, why don't we use LSTMs instead of RNNs? So for everything that I've talked in this particular talk, we are actually using LSTMs, and particularly we're using GRUs. I just basically, RNN is more of a general concept, right? It's a recurrent neural network, and LSTM is one instance of an RNN. So we're definitely using LSTMs and GRUs just because they have these cell mechanisms that allow us to actually propagate some or actually optimize these models much better, right? So we are using LSTMs and GRUs pretty much every time we're looking at the encoding of the documents or query, or anytime we're looking at reasoning. So let me just maybe quickly one more question. Are you hopefully that meta-learning techniques would work in NLP tasks, like, say, text classification? Yeah, absolutely. I think that the meta-learning algorithms are gaining more and more popularity right now, right? And I think that one of the things that I mentioned, I think in the last part of the talk, is this idea of learning from few examples, right? And that's exactly where meta-learning techniques could help us a lot for NLP tasks as well. In many domains, if I'm trying to do classification, I might have, in one domain, I might have lots of different examples. In a different domain, I might have just fewer examples. And the meta-learning techniques can help us, right? Because you have these base tasks, and you can leverage information from one task to another task, and really be able to maybe solve this new task, this new classification task in a particular new domain using meta-learning. So I think that's a very interesting area of research, and we see more and more papers in that space. I myself haven't really worked in that domain that much, but we did look at the problem of a one-shot recognition from images. and trying to look at the multimodal data where you have multiple modalities and try to leverage that information, this additional information in order to help us solve the one-shot task. In text classification, imagine that I give you a new domain. I'm trying to classify something in this new domain, but I might have some other modality, maybe sound or maybe images for this new domain. This is something that we've worked on, and I agree with you. This is a really, really interesting example of very interesting area of research in NLP. So NLP, I think, is itself is really, really exciting area of research, and we've seen some success stories using deep learning, but we're still very far away from this important area of research, which is reasoning. I think that's something that we haven't really done a really good job at, and I think that's the next step for us. So a lot of deep learning today is mainly focusing on pattern recognition, right? So for example, in classification, even in text classification, I can come up with some features in a sentence and classify the sentiment of the sentence, which is an important task. But once I go to more complex systems, like being able to ask complex questions about a document or something about, in general, being able to reason, kind of like solving SAT scores, so solving GRE, right? Many of you who are thinking about going into the grad school, you have to solve, you have to take a GRE test, and you might know that, there's a reading comprehension task where you have a text and you're trying to, answer questions about the task. And people are very good at doing that. Machines are very, very bad at doing that. So that's kind of the next frontier, at least the way that I view it in NLP. Okay, so on that note, let me just see if I missed any of the questions. But I will definitely make the slides available online. And one thing that I also wanted to mention is that at Carnegie Mellon, we are always looking for strong PhD and master students, and there is a lot of interesting research. So if you are interested in applying for a PhD or for masters, feel free to apply, because I think that it's it will give you a lot of and machine learning is a very exciting area of research. So it's the right time to do PhD in that domain. All right. Well, thank you so much, everyone. And if you have any questions, feel free to shoot me an email, and I'll make sure that I'll put the slides online and make it available to for all of you. You should also look on my webpage as well as on some of the papers. Everything that I've talked about today, there is a code online for most of it. Most of what I've talked about today, there's a code online, so you can download the code, you can play with the code, and you can pretty much reproduce all of the results that we have. Great, thank you. Bye.